Okay, so we have a trolley of mass 2 kilograms. It is initially at rest at the bottom of a runway that is inclined at 25 degrees. It is pulled up the slope by a constant force of 100 newtons. It travels 8 meters up the incline and the trolley experiences a constant frictional force of 50 newtons. Alright, so let's draw a free body diagram of all these forces acting. So we have our little object. Firstly, we know is being pulled up by a force equal to 100 newtons. It travels 8 meters and it's also going to experience a constant frictional force of 50 newtons. We also know that it has a mass of 2 kilograms. That means it'll have a force parallel to the slope acting downwards. So we can add that here. And that's going to be our FG parallel. And we will calculate that soon. Okay, so those are the main forces that act on it while it's moving up the slope. Okay, so now let's put the information in. We've got a 2 kilogram object. It is being pulled 8 meters up that slope by a force of 100 newtons, which is going to be pulled in that direction. Okay, so firstly we need to work out the net work done on the object. So let's look at our first method. So method 1, getting net work. So the first option is to just simply calculate each individual work done by each of the forces acting. So let's start with the amount of work done due to the force pulling it up the slope. So our work due to the force applied is equal to the force applied and the distance it was applied for. Now we can see that it's being applied parallel to the slope, or parallel to the motion, and so cos theta in this case is not really relevant. So we're going to have 100 newtons for a distance of 8 meters, meaning that the work done due to that force is then going to be 800 joules. We then need to calculate the work done due to friction. So our work due to friction is going to be the force of friction times the displacement that that friction was applied for. So force friction is going to be equal to, and so we had 50 newtons over 8 meters, meaning that we will get 400 joules due to friction. The next thing we need to work out is then the work due to the parallel, or FG parallel. So work due to FG parallel is going to be equal to FG parallel times the displacement that that work was applied for, or that that force was applied for. So FG parallel is going to be mass gravity times sine theta times the displacement it was applied for. So our mass 2 kilograms, 9.8 sine, and it is at 25 degrees times the displacement, which means that we will then get 66.27 joules. Okay, now we can see everything here has been unsigned so far. So we need to apply our signs to this. Obviously, these two are going backwards and that is going forwards. And so we can make that negatives. Therefore, the net work is going to be work due to the force applied plus work due to the frictional force plus work due to the parallel force. We add these up, 800 plus minus 400 plus minus 66.275. And we will get our final answer of 333.73 joules. Right, so if we look at this, we can see that that is applying all the work to pull the object up the slope. We then have the frictional force, which is taking work away from it, in other words, slowing it down or taking energy away from that object. And we also have the force of parallel gravity, and so that's also taken away, and so we land up with a net force of 333.73 joules. So method 2. Now, where previously we worked out the individual works due to each force, we're now just going to work out the net force and then substitute that into the net work equation. So net force is going to be equal to the force being applied plus force due to friction plus Fg parallel. Okay, so if we expand that out, it's going to be force applied plus force due to friction plus mass gravity sine theta. Okay, so our net force, or our force being applied, 100 newtons, plus our frictional force, which would have to be a negative 50 newtons, plus our mass gravity, which is going to be 2 times negative 9.8 sine 25 degrees. Right. If we do the calculation, we will get to a final answer of 41.72 newtons. Once we know how many newtons are being applied to this object in total, we can then use net work is equal to our net force times the displacement of the object. And so our net force is 41.72 times 8, and 41.72 times 8 will give us an answer of 333.73 joules. I personally prefer this method. I feel that doing each individual network equation or each individual work equation is just a little bit more tedious than just finding out what the net force is acting on the object and substituting that into the equation. And the last thing we need to do is find out what the velocity would be. So we now know that the net work done on the object was 333.73 joules. Therefore, if we want to find out what the velocity is at this point, we just need to use the work-energy theorem. And so, work is equal to the change in kinetic energy. So, our net work is therefore equal to half mass final velocity squared minus half mass initial velocity squared. Our net work was 333.73 joules. Half of the mass of 2, our final velocity squared. Our initial velocity, it was at rest, and so that's just going to be 0. Therefore, we can solve this to give us our final velocity, and that is going to then be 18.27 meters per second.